Hey guys, Miss Carr here. So today we are going to be talking about instantaneous rate of change. Before we do that, let's read through our I can statement. I know normally you guys read through it, but I am reading it for you today. So it says, I can use limits to find the instantaneous rate of change of a function. And we're going to get to the limit portion of that in a moment. Before we do that, I really kind of want to recap a little bit of what we did yesterday and then connect it to today's lesson. So yesterday, as a reminder, you looked at the average rate of change. So we had seen this before in previous classes. Essentially, our average rate of change was just that slope formula, which we all know and love, y2 minus y1 over x2 minus x1. However, we kind of elevated this formula a little bit yesterday, and we talked about it in terms of the function itself. So this blue line over here, we have our function, and what we did, we labeled these 2 points. Okay, we had these 2 points that we were creating a secant line from. Remember, a secant line is just a line that connects through a function in 2 separate spots. Okay, and what we did, we labeled this one as point A and this one as point B. And what that allowed us to do was that also allowed us to label our y values. So that meant that here for our y value, drawing straight lines are hard, we had f of A, and here our y value would be f of B. So these are labeled with values, but we could also label them as A, f of A, and B, f of B. And then what we did, using that piece of information, we recreated this slope formula that we know and love. And we rewrote it as f of B minus f of A all over B minus A, which still was talking about the change in our y values over the change in our x values. So all 3 of these things on my screen at this moment, those are all synonymous with one another, essentially saying we're looking at our change in y compared to our change in x, and you're giving me this slope over a specific amount of time. So that was what we looked at with average, and specifically we saw that word secant that maybe we hadn't seen since geometry. Well, let's imagine now for a moment that instead of average rate of change, I now want to know the instantaneous rate of change. I want to know exactly what's happening at a very specific moment. Before we do that, I want to reimagine this formula one more time. So you'll notice that instead of A's and B's, now I'm using x and x plus h. What that does, that allows me to label this change between our 2 x values as h. So essentially the distance between these 2 x's is h, and that's why I'm allowed to put x plus h on this right-hand value. Okay, so now instead of f of b minus f of a all over b minus a, I can now use a new formula, and this green dot up here would be labeled f of x plus h, and this red dot over here would be labeled f of x. So my formula now would be f of x plus h minus f of x all over x plus h minus x. And that's simply just from relabeling. Instead of A's and B's, I've relabeled them with x and x plus h, saying that h is the distance between those 2 x values. I haven't changed the formula, I've just rewritten it another way. And now hopefully you guys are seeing here, hey, there's something I could do to simplify this. Absolutely, let's do it. So now my numerator would stay the same, and my denominator, since I have these 2 x values, I can eliminate those, and I just have an h now in our denominator. Okay, so this is our new formula that we're going to want to get super comfortable with. So we've now really talked about 4 different ways we can represent this average rate of change. With different formulas, same idea. Now let's kick it up a notch and instead of average, look at instantaneous. Okay, you'll notice that I've already written our formula here that we're going to use, but I want to talk about it for a moment. Because what average was doing, average was looking at the secant line between 2 points. If I want to know the instantaneous, what I'm going to want to do is I'm going to want to move these points closer and closer together until essentially we have one spot on our graph that we're looking at. And that would give us our instantaneous rate of change at that one location. Now, if we're moving closer and closer, remember we had talked about our distance between our 2 x values. This was labeled h as our distance. If we're moving these 2 values closer and closer together, essentially what we're doing, we're wanting h to get closer and closer to 0. And in our last unit, we had discussed a way that we could talk about this. Think of that word approaches. When we hear the word approaches, we think limits. So we want h to approach 0. So if I'm talking about instantaneous rate of change, if I see this word, that's going to be our key that we're not just looking at a ratio anymore. We're now stepping it up a notch. If I want instantaneous, I want that h value to be close and approaching 0. So now I'm going to describe that with limits. I'm going to say as my distance between those 2 x values approaches 0, I want to then compare them with this formula. Okay, and this is my new thing. I want you to write this down, highlight it, star it, box it off, whatever you need to do. This is our big formula that we're going to use today. And again, this is to find our instantaneous rate of change at a point. Right? So let's put this into practice. I have an example here. I'm given a function, and it wants me to find the instantaneous rate of change at x equals -1. So essentially what I'm doing is I'm looking at that point, x equals -1 on my graph, and I'm going to use the formula that we've just discovered, and I'm going to really implement it with our function here. So I'm going to rewrite that formula just so we have it as a reference. Okay. And now what I'm going to do is I'm going to plug this in. So when I see f of x plus h, what's happening is I'm plugging in that x plus h every time I see an x in the function. So I'm going to rewrite this original f of x, but instead of an x, I'm going to put x plus h every time. So here we go. The limit as h approaches 0 of 2, instead of x, I'm putting x plus h squared plus x plus h. So that was this portion, what I just wrote out. Now I need to just write f of x. So now I'm going to do minus, and since it's just f of x, I just keep it as an x. I don't have to put x plus h. And that's all over h. Now ideally we'd like to use just direct substitution, but as we can tell, if I were to plug in a 0 like my limit tells me right now, I'm going to have some issues. So instead what we're going to do is we're going to distribute, we're going to simplify, we're going to see what we can do here. So I'm going to actually kind of go through and FOIL that x plus h out. So here we go. When we FOIL that out, I'm going to get x squared plus 2xh plus h squared plus x plus h minus 2x squared plus x. At this point, I'm going to keep simplifying. Oh, I still have that h. I'm going to drop my limit just for a moment, just for the sake of writing. So here we go. I just realized Ms. Carr made a cardinal mistake. I subtracted f of x. I forgot to put this in parentheses. That means this should really be a minus x. That is my fault. Bad, Ms. Carr. But what that's going to allow me to do is to cross some things out. So I can kind of get rid of this x, get rid of this x. I can also get rid of these minus 2x squareds and the positive 2x squareds. Those are opposites of one another. And then I'm left with 4xh plus 2h squared plus h all over h. Okay, so now what I'm going to want to do, I want to get rid of this h in the bottom. I'm going to try and take out an h from every term in the numerator. So let's take out our GCF here. And now I don't have a problem. If I go back and I think about my limit, now there's no 0 in our denominator. I just have 4x plus 2h plus 1. So when I plug in our 0 for h, I'm going to be left with 4x plus 1, because what it really does, it makes this h 0, which eliminates that term. So our instantaneous rate of change. Now let's talk about what we just found. This is our instantaneous rate of change for the entire function. Instantaneous, there we go, rate of change. That's our instantaneous rate of change for the entire function. So at any point, if I'm looking at this f of x function, I can use this 4x plus 1 to help me find the instantaneous rate. However, I want to know specifically at x equals -1. So now what I have to do, I have to take it one step further, and I have to plug in -1 for my x. So now 4x plus 1, when I'm looking at x equals -1, it's going to be 4 times -1 plus 1, which would just be -3. So our instantaneous rate of change at x equals -1 is -3. Now let's talk about what that means on our graph. This was our function, our f of x equals 2x squared plus x. And what we did, we looked at x equals 1. So we looked at our point right here. And we found our instantaneous rate of change. And what that would look like on a graph, it would be what we call, this is our new vocabulary word, this would be a tangent line. Okay. It barely touches that function. It's kind of hard to draw, but it barely touches this function, and then it goes away. Our secant line, remember, touched in 2 places. A tangent line only touches in 1. So we can describe what we just found in 2 ways. We can describe it, 1, how I've been saying it, the instantaneous rate of change, or we could describe it, and you'll hear this quite often, the slope of the tangent line rather than the secant line. And what we described, our slope of our tangent line, so our slope at this point on our function, what's happening right at that spot, we have a slope of -3 at that point. Right? All right, so just to recap real quick, I wanted to make sure everybody knew the difference between our secant and our tangent. Here's another description. Our secant is the line connecting 2 points. Tangent, you can see right here, it touches this spot and then it goes away. It barely touches the function at one location, and it tells us what's happening right at that very spot. Okay, then let's take this one step further. I promise this is it. If I want to find the equation of the tangent line at x equals 1, and let's continue on with our function. We had f of x equals 2x squared plus x. That was our original function. But now, instead of just the rate of change, I want to know the full equation. So we already know our slope at that spot. I know that our slope is -3. We already found that. However, if I want to know the equation, I'm going to use our point slope formula, which is y minus y1 equals m times x minus x1. My cat is ringing a bell. I'm sorry. Harley. Okay, so now I'm going to plug everything in. I have my x value at x equals -1. So I have y minus, I have my m, which is -3. Remember, we don't plug anything in for our x or our y without a subscript. I have my x sub 1 is -1, so I'm actually going to put a +1 because there were two negatives there. What I don't have is this y1 value. Well, that's easy enough to fix. If I want to get a y1 value, just go back to the function itself. So now f of -1, remember to get our y value, we're just going to plug in our x. 2 times -1 squared plus -1. So f of -1 is 2 minus 1, which is just 1. So I'm going to plug in 1 for my y1 value. Okay. And now we could leave it like this if it does not specifically ask for slope-intercept form. However, if it does ask for slope-intercept form or y equals mx plus b, we are going to go through and simplify it. So I'll show you how to do that as well. Here we would just distribute and then move that last value over. And you have two ways of writing your equation of the tangent line. Right? I hope this helped you guys understand instantaneous rate of change, slope of tangent lines, and equations of tangent lines.